we're going to learn a little bit about the periodic table, okay? And you see the electron configurations match the periodic table real good. The first periodic table actually was Mendeleev. I know they talk about this German fellow, but Mendeleev has been credited. What he did, he realized that there was a periodic relationship between the properties of the elements. He had originally a list of elements by atomic number, but he realized that certain properties repeat themselves periodically, every so many elements, and all of that. So he got a long list and cut it with scissors in pieces and put the elements one on top of each other where they match the properties. And that was the earliest periodic table. So for instance, lithium, sodium, potassium, they all are shiny, conduct heat, they have similar chemical properties, so they were put in the same column, and the same thing. That left some gaps, but that was the first periodic table. Whenever an atom did not match, he would cut and move it in the periodic table. So he just had them in columns that have similar properties. That left some gaps, like I said. So he predicted there would be some elements, for instance, that have properties similar to aluminum and silicon, but they were not known. And because of the position in the periodic table, he actually predicted things like density, he predicted melting points and boiling points, he predicted reactivity, and he was right on the money. Eventually they discovered gallium and germanium, and the properties match what Mendeleev has said. Those elements that didn't exist at the time, or were not known at the time, he said, when we discovered, that's how they're going to look like. And he was right. So people started taking him seriously at that point. By 20th century, when there's a periodic relationship between the atoms, he was mostly classifying them by atomic numbers, which usually match very well. But we said that the properties are periodic functions of the atomic numbers. We have a Moin periodic table that arranges the elements in periods, horizontal rows in there, and groups that are vertical columns. Every element in the same group has similar properties, and their number, UPAC wants a number 1 through 18. It used to be the US system, but unfortunately the UPAC has put enough pressure that it's going away. Okay, so this is the periodic table. I do have a big copy of it that if you make an appointment through Wysant, I'll be able to send it to you where you can print it. You can even print it in color, put it in a sheet protector or laminate or something like that and use it. I like this one. There's many periodic tables, okay? I'm not saying you have to use mine. I picked this one because it uses the modern numbers for the periods. It has different colors for metals, non-metals, transition metals. It gives you the atomic number, atomic mass, and it also gives you, if you can see it bigger, it gives you the name. Not only has the symbol, but it gives you the name, which is very useful. You can see it here in halogen. Okay? When you're learning, it helps. Eventually, you will need to be looking at the names, but at the beginning, it does help. But it has all of the information that you need and no extras. Some periodic tables will add a bunch of extra stuff, and it's difficult to find things when it has too much. This is just the perfect combination, gives you everything you need, but not a bit extra. You can print it directly from the PowerPoint, but like I said, I can give you this periodic table. We say that we classify them. You can see on yellow, you have metals. On the right, in green, kind of green, non-metals, and then in pink, you have metalloids. Metals are known because they are shiny, malleable, meaning that if you hit them, they don't break, they bend and all of that. You can get a chunk of aluminum and you flatten it with a hammer. It doesn't necessarily break, it just flattens. Ductile means that you can stretch it in wires and all that. They're good conductors of heat and electricity. Non-metals on the left, they're dull, they're poor conductors, and we are going to see when we talk about bonds that they're actually brittle, they break easily. And metalloids are between metals and non-metals. So they have some properties of metals, some properties of non-metals. They're relatively good conductors, but not as good as metals. We also classify them by the groups. And I wish I could put the periodic table in here. But the main group elements, let me go back to the periodic table, are groups 1 and 2 and 13 through 18. What's left in there, that's the part that seems to sink in a little bit. Those are transition metals. Okay, so 1, 2, 13 through 18, we call them main group elements. Some people call them representative elements. In the middle, you have the transition metals. And then going back to the bottom, you have the inner transition metals. The first group is called the lanthanides because it begins with lanthanum, actinides because it begins with actinium. Okay, lanthanides and actinides. So all that is in writing there. These are names that you need to know. I'm not expecting you to memorize the periodic table, but if I'm asking you, I like to ask a question. Tell me the name of a transition metal that's in the fourth row. There's a bunch of answers. But if you answer a regular metal, a main group element, that's not a transition metal. You need to know these terms, okay? There's also a few groups, just 4 groups, that have a name. Group 1 are called alkali. Now, alkali metals do not include hydrogen. Hydrogen is one of those elements that you really don't know where to put it, because you could put them in group 1, and most periodic tables today do that, because it has 1 valence electron. But I've seen people putting them in group 17 because they're short of 1 valence electron to make a noble gas. And I've seen periodic tables where actually they had the periodic table and they put hydrogen fluorine in the center. I kind of like that because it reminds me hydrogen is an exception. Look at hydrogen is not perfect for 1, it's not perfect for 17. So, but your book puts it in 1, that's fine. But it's not a metal, hydrogen, okay? Group 2 are called alkaline earth metals. Be very careful not to confuse the 2 names, they're similar. Alkaline earth. I have people telling, oh, this is an alkaline, or this is an alkali earth. Please be careful with the terms. Group 17 are the halogens, and group 18 are the noble gases, the ones that have an outermost shell full. Okay? So we are going to see that the periodic table arranges atoms, so the elements in the same group have similar properties, chemical and physical properties. Why? Because they have similar valence electron configurations. Remember we said everything in group 1 had an S1. It could be 1s1 or 2s1 or 3s1, but they were all S1. In group 2 they were S2 and all of that. And this is important because it is the valence electrons that are important in chemical reactions. So having the same number of valence electrons explains why they have similar reactivities. When we talk about the main group elements, we say that they're filling either S or P orbitals. The metals or groups 1 and 2 are filling S. The non-metals are going to be filling P orbitals and all of that. So the valence electrons are going to be the ones that have the highest value for N. So for instance, gallium, be very careful because a lot of people will say valence electrons 1, 4p1, that's the highest. No, it's the highest N. N4, so 4s2 and 4p1. Those are the valence electrons. Yes, 4p1 has high energy than 4s2, but both of them had the highest principal quantum number. So you have 3 valence electrons. Okay? And this 3d10 that are left in there, they're still part of the core. But other than being careful, highest N, no problem with that. Transition metals, oh boy. Then we go back to the d orbitals. So the valence electrons include the highest N and the highest D that is 1 number lower than D. So vanadium, 4s2, 3d3, all 5 are valence electrons, even though they're in different high energy levels. Okay? And if that wasn't complicated enough, sometimes they're going to choose to treat different some disks from others. So this is a general rule. Valence electrons are going to be the last two, the S and the Ds, but we are going to see that they're going to break this rule whenever they feel like it. In the transition metals, you're going to include, remember, those are the actinides and lanthanides and actinides, so you're going to include the S, the F, and D, if there's a D in between them. Like in this particular case, promethium, there's no D, but the S and the F, those are going to be the valence electrons. Yes, it can be confusing. You know what to do. Make an appointment through Wysant. The link is in the video description, and let me help you.